Okay, let's jump into this. Imagine a computer looking at, well, any single photograph, maybe from your phone, a security camera, even a 360-degree lens, and instantly understanding the full, precise 3D layout.
Yeah.
Everything in that image, just like our own brains seem to do, effortlessly.
That's the dream, right? Monocular 3D estimation, MDE. It's absolutely fundamental for intelligent systems. Think autonomous vehicles, robotics, AR.
Crucial stuff.
Definitely. Even creating 3D content.
Right. But here's the reality check. Getting that 3D view from just one image, it's been incredibly hard.
Yeah.
And a huge part of the problem, it seems, is that most existing methods are kind of stuck using old, really simplified camera models.
Yeah, the classic pinhole camera assumption, or they force you to warp the image first, rectify it to make it look like it came from a pinhole camera.
And that's where things just, break down in the real world, isn't it? Because cameras are not all pinhole. You've got wide lenses, fisheyes, panoramic views, all sorts.
Exactly. And those older methods, because they're tied to those simple models, they just can't handle the complexity and, frankly, the distortions you get from real-world cameras. Not effectively, anyway.
Their performance just tanks, especially when you need actual metric 3D, real distances, real sizes in the world. And trying to estimate the full 3D geometry, not just a vague depth map, becomes almost impossible with those rigid assumptions.
And there's a deeper issue, too, a mathematical one. For cameras with really wide fields of view, say, anything over 180 degrees, the traditional way of predicting depth, the perpendicular distance from the camera plane, it becomes fundamentally unstable. Technically ill-posed, especially for things way off to the side.
Okay, ill-posed. So unstable, unreliable.
Pretty much. Prone to big errors.
So you've got methods that are rigid, they can't handle all these different cameras, they lose important 3D context, and they hit these mathematical walls with wide angles. The big challenge then is, can you build a system that sees any image from any camera without needing to know about that camera beforehand and still give you accurate 3D?
And that's exactly where UniK3D comes in. Based on the source material we're looking at, it's presented as a really significant academic step forward, a universal framework designed specifically for this estimating accurate metric 3D from a single image, no matter the camera type, and crucially, no prior camera info needed at test time.
Okay, so our mission for this deep dive is to really pull out the core, innovative ideas from your sources, the academic breakthroughs that make this universal thing possible. What are the technical nuts and bolts, the novel concepts that let UniK3D break free from those old limitations? Let's get into the weeds a bit.
Absolutely. The sources lay out several key innovations, real departures from previous approaches.
All right, so let's start with that mathematical hurdle you mentioned. Why is predicting depth such a headache for wide-angle cameras, especially the really wide ones, over 180 degrees?
Okay, picture a point way off to the side in a super wide image, like from a fisheye lens. If you're trying to measure its distance perpendicularly back to the camera's main viewing axis, tiny errors in figuring out its angle in the image can lead to huge swings in that calculated perpendicular distance.
Ah, right. Like a small angular error gets amplified way out there.
Exactly. The measurement becomes super unreliable. It's a bit like trying to judge how far away something is by looking at it just from the very corner of your eye. Small mistakes in judging the angle make a massive difference to how far away you think it is straight ahead. It's numerically unstable.
Okay, so depth breaks down at the extremes. How does UniK3D get around this? What's their approach to measuring distance?
That's their first big innovation, and it's a fundamental shift.
Wow.
Instead of predicting that perpendicular depth, UniK3D represents the scene's range dimension using radial distance.
Radial distance, so
Okay.
distance from the camera center straight out to the point in 3D space.
Precisely. The distance along the actual ray of light that corresponds to that pixel. And this is critical because radial distance is numerically stable everywhere on the sphere. It doesn't suffer from that instability issue at wide angles that perpendicular depth does.
Huh.
The sources really emphasize this. This shift lets them handle, theoretically, arbitrarily wide fields of view, even full 360 panoramas, without the math falling apart.
Okay, that makes sense conceptually. And the sources mention something about projected objects varying univocally with radius. What does that mean, and why does it help the network learn better?
Right, that's a key insight they leverage. Think about how an object size appears in an image. With a standard pinhole camera, how big something looks depends on its distance and its angle from the center. It's a complex relationship,
Yeah.
Two objects at the same depth at different angles might look differently scaled.
Yeah, perspective distortion, foreshortening, all that jazz.
Exactly, but if you think about it in terms of radial distance, the distance along that specific light ray, the relationship between the object's apparent size in the image, specifically how it projects onto a spherical view, and its actual distance along that ray is simpler, more consistent.
Simpler how?
It varies univocally, basically. There's a more direct one-to-one correspondence. The apparent size along that ray changes predictably just with the radial distance along that ray, without being complicated by those angular effects in the same way depth is.
So the network has an easier job figuring out how far away is this thing along this specific direction, just by looking at image features around that point, because the relationship isn't getting tangled up with complex perspective effects.
That's the core idea, yes. This property makes the learning task more tractable for the network. It's easier for it to learn how to estimate accurate 3D geometry across the entire field of view, especially compared to learning the complex angle-dependent relationship needed for depth prediction.
Okay, cool. So representing the 3D world spherically, using radial distance, that's innovation number one, a big one. What about the camera itself? You said old methods predict specific parameters like focal length, assuming a model. How does UniK3D handle the camera universally?
This is innovation number two, and it's really quite novel academically. Instead of trying to predict the camera's specific parameters, its blueprint, essentially, UniK3D directly models the set of viewing directions for all the pixels, what the paper calls the pencil of rays.
So the direction in 3D space that each pixel is effectively looking.
Yes. And crucially, they don't model this using explicit parameters like focal length or distortion coefficients. Instead, they represent this entire, potentially complex angular distribution using a learned combination, a superposition of spherical harmonics.
SH.
Spherical harmonics. Okay,
Yeah.
that sounds pretty mathematical. Can you break that down a bit? What are they doing?
Think of it like this. You know how you can represent a complex sound wave as a sum of simple sine waves?
Yeah, Fourier analysis. Right. Spherical harmonics are kind of the equivalent for functions defined on the surface of a sphere. They're a set of basis functions. You can represent any smooth function on a sphere by adding together different amounts of these basic spherical harmonic shapes.
Okay, so the camera's pencil of rays, that mapping from pixels to 3D directions, is basically a complex function spread over a sphere. And UniK3D uses SH as building blocks to describe this function.
Exactly. The network doesn't output a number for focal length. Instead, it outputs a small set of coefficients numbers that say how much of each basic SH shape to use. The sources say just 15 coefficients for a third-degree basis. These coefficients effectively tune the overall pattern of rays.
And that allows it to represent any camera.
That's the power of it. It can represent the viewing geometry of pretty much any camera pinhole, fisheye, panoramic, even catadioptric systems, just by learning the right combination of these SH coefficients.
That's a totally different way of thinking about the camera model. It's not guessing the model type, it's learning the shape of the viewing field directly. Why is using SH coefficients better than trying to predict, say, fisheye parameters?
Well, first, it's inherently model independent. It makes no assumptions about the camera type. It's assumption-free, as the paper puts it. Second, it's compact, just a few numbers describe the entire complex geometry. And third, mathematically, SH functions have really nice properties. They're smooth, continuous, differentiable, which is great for training deep neural networks. Trying to predict discrete parameters or parameters with weird interactions can be much harder for a network to learn. This SH approach gives the network a flexible, continuous space of camera geometries to explore.
So radial distance for what it predicts the 3D points and spherical harmonics for how it represents the camera that took the picture. These seem like the two really core academic shifts here.
Precisely. They tackle the output representation and the input camera modeling simultaneously with these spherical approaches.
Okay, let's touch briefly on the architecture. How does the network actually put these ideas together?
It uses a fairly modern transformer-based structure, but with specific modules designed for these tasks. First, you've got an encoder backbone. This is a vision transformer, a VIT. It takes the input image and chews on it to extract features, both detailed, dense features across the image and some global summary tokens. Pretty standard first step these days.
Right, image goes in, features come out. Got it.
Then there's the angular module. This takes those global summary tokens from the encoder. Using transformer encoder layers, its job is to predict those crucial spherical harmonic coefficients, plus a couple of other high-level parameters. Basically, this module figures out the camera's overall viewing geometry, the angles for all the pixel rays.
This is where the SH coefficients get predicted, the camera modeling part.
Exactly. Now, in parallel, you have the radial module. This module takes the detailed features from the encoder, the ones corresponding to different parts of the image. And here's the key part. This module is conditioned by the camera ray information that the angular module just figured out.
Conditioned. What does that mean in practice? How does it use that camera info?
It uses transformer decoder layers, employing cross-attention. You can think of it like this. The decoder asks, okay, for this specific pixel location, the query, what are the visual features here? And D, what is the camera ray direction for this pixel? The keys value is coming from the angular module. It combines this visual information with the geometric information from the camera model.
Ah, so it's using how the camera sees information directly when figuring out how far away things are.
Precisely. This conditioning step is vital. It injects the specific projective geometry derived from the SH coefficients into the process of estimating the distance along each ray. It forces the distance estimation to be aware of the camera's properties.
So angular module figures out the camera geometry, angles, passes that info to the radial module, which then uses that geometry, plus the image features, to predict the distance along each ray.
That's the flow. The radial module refines these conditioned features, often using something like a feature pyramid network structure for multi-scale processing, and finally outputs the radial distance for each pixel, usually in log space for numerical stability. Combine the angles from the angular module and the log radius from the radial module, and boom, you have the full 3D position for every point.
That structure makes sense. But even with clever architecture and these new representations, training deep learning models can be tricky. Real-world data is often biased, right? Lots of normal photos, fewer weird ones. The sources mention a problem called fovea contraction. What is that, and how do they tackle it?
Yeah, fovea contraction is a classic training problem. If most of your training data comes from cameras with a standard narrow field of view, the network naturally learns to just predict narrow field of view outputs. Even if the architecture could handle wider views, it sort of defaults to the common case. It learns to shrink its predicted field of view because that minimizes errors on the bulk of the training data. It underrepresents or ignores the wider angles.
So even though the model could be universal, the training data bias pulls it back towards the mundane, the standard pinhole-like view. How do they fight against that tendency?
They came up with two really interesting, quite innovative training strategies according to the sources. The first one is an asymmetric angular loss.
Asymmetric loss, meaning it penalizes some mistakes more than others?
Exactly. Specifically for the polar angle part of the camera ray prediction, basically, how far a ray is from the center. It's based on something called quantile regression. The core idea is they make it much more costly for the network to underestimate a wide angle, predicting a narrower fovea than reality compared to overestimating it.
Why would you do that? Why punish underestimation more?
To actively push the network to be braver, you could say, to force it to predict the full, wide field of view when the data suggests it should. It tells the network, look, it's much worse to miss capturing the wide view and predict something too narrow than it is to slightly overshoot and predict an angle that's a bit too wide.
So it essentially counteracts the data bias by making errors in one direction, the direction of contraction, much more painful for the network during training.
Yes, precisely. It provides a direct learning signal to preserve the wide angles. The sources call this a more direct and efficient solution than trying to do complicated dataset rebalancing or resampling, which can be tricky to get right.
Okay, that's a clever use of the loss function. What's the second strategy they use to make sure it handles wide angles robustly?
That involves enhanced camera conditioning. They realized it wasn't enough for the angular module to just predict the camera geometry. They needed to make absolutely sure the radial module actually used that information effectively, especially early in training when the angular module's predictions might still be a bit noisy or uncertain.
Why? Couldn't the radial module just learn to guess distances from features alone?
Well, it could try, especially for simple scenes or standard foveas. But if it learns to ignore the camera information provided by the angular module and just relies on visual cues, it completely loses the ability to generalize to different unseen camera types with unique projective geometries. It wouldn't be universal anymore.
Ah, I see. So they had to force the distance predictor part to actually listen to the camera geometry predictor part.
Exactly. They employed several techniques to achieve this. One really notable one mentioned is a form of curriculum learning.
Curriculum learning, like starting with easier lessons before moving to harder ones.
Sort of, yeah. They start training the radial module by feeding it the perfect ground truth camera information for the training images. So the radial module first learns the core task. Predict radial distance, given you know exactly how the camera saw the scene.
Okay, learn with the cheat sheet first.
Right. Then, gradually, over the course of training, they reduce their reliance on this perfect ground truth information and start feeding the radial module the camera geometry actually predicted by the angular module.
Ah, so it learns the main job with perfect guidance, and then it learns how to do that same job using the potentially imperfect guidance from its partner module. That makes a lot of sense.
It helps stabilize training and ensures the radial module learns to interpret and use the angular module's output effectively. The sources also mention some other related tactics, like detaching gradients between the modules in certain ways and being careful with learnable gains in the conditioning layers. It's all aimed at the same goal: making sure the radial module must leverage the predicted camera geometry and can't find lazy shortcuts that ignore it. This really bolsters the robustness needed for diverse, large FOVs.
So it really sounds like it's not just the novel representations, the radial distance and SH camera, but also these quite sophisticated training techniques that are key to preventing the model from just collapsing back to the simple cases it sees most often.
Absolutely. These training innovations seem just as crucial for achieving that claimed universality and generalization to unseen camera types in the wild.
Okay, so these academic ideas, the spherical representations, the SH camera, the clever training, it all sounds great on paper. But the real question is, does it actually work? What's the proof in the performance? How does UniK3D actually stack up when you test it, especially on data it hasn't seen before?
Right, and that's where they focus their evaluation, particularly on zero-shot generalization. That means testing the trained model on datasets with camera types or scene distributions it was never explicitly trained on. That's the gold standard for checking if something is truly universal.
Okay, the acid test. So how did it do?
According to the sources, they tested UniK3D across a broad range of 13 different datasets. These covered everything from standard pinhole camera datasets to datasets with significant lens distortion, large fields of view defined as over 100 degrees, and even full 360-degree panoramic datasets.
A pretty comprehensive test suite. And the results?
State-of-the-art performance pretty much across the board. But the really striking results were in those challenging categories: the large FOV and the panoramic datasets. That's where methods based on older assumptions really tend to struggle or fail outright.
How significant were the gains there? Are we talking small improvements or?
No, quite substantial gains. The sources highlight this specifically. For instance, on the large FOV datasets, UniK3D reportedly outperformed the previous best methods by significant margins, quoting numbers like over 20% and even over 40% improvement on key 3D accuracy metrics, depending on the specific dataset and metric.
Wow, over 40% on some metrics for large field of view data. That's not incremental, that's a leap.
It really seems to be. And on the panoramic data, the improvements were described as even more dramatic. It strongly suggests that their core innovations, the spherical representations, are paying off exactly where they should in handling those extreme viewing angles where traditional depth and pinhole models break down.
And a really crucial detail you mentioned earlier, it achieves this without needing any camera information fed to it at test time. No telling it this was taken with a fisheye lens.
Correct. That's a major point emphasized in the sources. You just give it the raw image. No ground truth camera parameters, no image rectification needed beforehand. Many competing methods required one or both of those, which limits their practical use significantly.
So you could theoretically feed it an image from your smart doorbell, your phone's wide-angle camera, a 360 cam, a drone, and it just figures out the 3D geometry.
That's the promise, and the zero-shot results strongly suggest they've made major progress towards that goal. Importantly, the sources also note that it maintains top-tier accuracy on the conventional small FOV datasets as well. So the improvements for wide angles didn't come at the expense of performance on standard images.
That's good. It didn't sacrifice the common case. And how does it compare to something like Unidepth, which was also aiming for generalization?
Unidepth was definitely a strong step towards generalization, but it was still fundamentally based on predicting perpendicular depth and implicitly used a pinhole assumption, even if trained on diverse data. This inherently limited its effectiveness, especially as FOV went much beyond, say, 120 degrees, and particularly over 180, where depth becomes ill-posed. UniK3D's fundamental changes the SH camera model and the switch to radial distance directly address these limitations, allowing it to push performance much further in those very wide-angle and panoramic regimes where unit depth would struggle more.
And they did internal experiments, ablation studies, to confirm that each of these specific academic innovations, the radial distance, the SH camera model, that asymmetric loss function, the enhanced conditioning strategies, were actually necessary.
Yes, the sources mention these ablation studies. They systematically removed or replaced each key component to see the impact on performance. The results apparently confirm that each of these novel elements provided a significant contribution, especially boosting performance on the challenging wide-angle datasets. It wasn't just one magic bullet, it was the combination of these innovations working together.
Okay, so wrapping this up then, UniK3D is presented in these sources as really the first framework that could genuinely claim to be universal for monocular 3D estimation. It seems capable of handling images from pretty much any camera type you throw at it, seamlessly.
And its success appears to stem directly from those core academic innovations we've discussed, fundamentally shifting to a spherical 3D representation using radial distance instead of depth, developing a completely novel, model-independent way to represent the camera using spherical harmonics, and designing these sophisticated training strategies, like the asymmetric angular loss and the enhanced conditioning, to overcome data bias and ensure the model truly learns to generalize.
So why should this matter to you, the listener? Whether you're deep into robotics, working in AR/VR, or maybe just fascinated by computer vision, well, it means we're getting incredibly close to having robust, reliable 3D sensing from just a single everyday image, no matter how or where that image was captured. This has huge potential to make 3D computer vision far more practical, deployable, and useful in the messy real world, which is absolutely full of diverse and often uncalibrated cameras.
Yeah, it potentially unlocks this vast amount of visual data out there from existing security footage, user photos, historical archives that was previously very difficult or maybe impossible to use for accurate metric 3D scene understanding.
So here's a final thought to chew on. If we can now reliably perceive the 3D world from almost any single image, what applications, previously stuck in the lab or just science fiction, suddenly become feasible? Think about robots navigating complex, unknown spaces using only cheap, perhaps distorted cameras. Think about autonomous systems gaining a much richer understanding from wide-angle sensors. Or even think about historians or archaeologists being able to reconstruct accurate 3D scenes from old photographs taken with long-forgotten cameras. This kind of universal perception could fundamentally change how machines see and how we use the visual data all around us.